Hey everyone, and thanks for tuning in again. Today's video will be about checking regression assumptions. So I'll be showing some approaches I use for checking assumptions, and remember, out of the Gauss-Markov +1 assumptions, only 3 can be tested with sample data, and these include homoscedasticity, independence of errors, and normality of errors. The approach I'll be showing is a quick and informal screening. So this is what I call my first line of defense. So in every data set, most assumptions are typically already violated to some degree. So the goal is really to see if it's bad enough to warrant further actions. So the main question is, does the evidence suggest that I need to worry about the results of my analysis being affected? So remember, when some of these assumptions are violated, it could bias our estimates, and it could also change, it could upwardly bias or downwardly bias our standard errors, therefore affecting statistical tests. And we don't want that to happen. So if the evidence does show that I need to worry about the results of my analysis being affected, I can follow up with more formal tests, which will be covered in other videos, the diagnostic videos. But if not, then I could just proceed with my analysis as usual. So there are many approaches and sets of approaches for assumption checking, and this is just what works for me. So ultimately, you can take and run with what works for you, and you can drop what doesn't. Assumption checking, whether formal or informal, are simply rules of thumb, which are usually not generalizable to all situations. So none of the rules that I talk about here are set in stone, and they change on a case-by-case basis. Sometimes, not all the experts even agree on what the rules of thumb should be. So the purpose of assumption checking is to build a compelling case that either shows that assumption violations will not affect the outcome of analysis or are not likely to affect the outcome of analysis, or that assumption violations have been addressed to an extent that the outcome of the analysis will no longer be affected. So again, the approach I show here is how I begin to gather evidence to build my case. And many times I'm talking about reviewers, my case for reviewers. So there may be a bit of overlap in this video with the regression diagnostics videos, but again, this is just a quick check, mostly based on visual inspection of graphs and plots. More formal statistical approaches for detecting assumption violations will be covered in the videos on regression diagnostics. So with that, let's go ahead and get started. Alright, so here I have SPSS open, and by default it opens up this blank data set. So what I'm going to do is I'm going to go ahead and open up my regdata3 data set. So again, I have mine stored on the C drive in a folder called datasets, and today we'll be using regdata3. Go ahead and pull that data set onto this screen. Here's my output viewer. I'll go ahead and minimize that for now. Alright, so this data set, we have 5 variables. We have x1, x2, x1 and x2, which are predictor variables, and then we have y1, y2, and y3, which are separate outcome variables. We have 150 observations. That's how many observations we should have. So it looks like everything here has read incorrectly. So we're good. So to start checking our assumptions, we'll begin with some descriptive statistics. So we'll go to Analyze, Descriptive Statistics. We'll select Descriptives, and then using Shift, I'm just going to go ahead and hold down the Shift button and click all the way down to Y3 to highlight all of the variables. Click here to put them in the variables box. And then for options, since I'm interested in checking how the distribution of the variables are, whether they're normal or non-normal, I'm going to go ahead and click kurtosis and skewness to add this to my descriptives. I'll click continue, and then we'll hit OK. Okay. And so the first thing I get are my descriptive statistics. A good place to look, the minimum and maximum. If you have any familiarity with the data set that you're using, it's pretty easy to spot whether the minimum goes too low or the maximum goes too high. So that's a good place to start, just to make sure there aren't any errors in reporting what the data points are. Input errors, that's the word that I was looking for. Okay. So for our purposes, we're interested in the distributions of the variables. Now remember, the assumption of normality is centered around the distribution of the residuals, or the error. It's not about any of the variables in particular. But one way to kind of see, or a proxy to the distribution of the errors, is the distribution of the outcome, or the criterion. So in this case, we wouldn't worry so much about the distribution of the predictors, x1 and x2, but we would be interested in looking at the distributions of y1 through y3. Now again, y1, y2, and y3 are separate outcomes for different models, but they're just all part of our one data set. And so looking at the skew and the kurtosis, a rule of thumb is plus or minus 3. So anything that goes above or below, anything that goes below -3 or above +3 is a cause for concern. But again, that's just a rule of thumb. In my own personal experience with simulating non-normal data, skew that is at about like over 1, that is at about 1.2 like we have here, could be cause for concern. So that's something that we want to make sure we take a look at. All right, so if we're looking at y1, none of the values look extremely high or extremely low. There's nothing lower than -3, nothing above +3, so that's okay. For y2, kurtosis seems to be a little high, but skewness seems to be okay. But again, 1.2 might indicate some non-negligible positive skew, so we'll want to take a look at that. Same thing for y3, we might want to take a look at that for the skew, but the kurtosis looks okay. All right, and so that's just our descriptive statistics. We're not looking at any one assumption yet, but it's just good to get an idea of how our different y variables are distributed. Okay, so we'll go back to our data set, and the next thing we're going to do is we're going to look at the first assumption that we can test within our sample. So we want to take a look at homoscedasticity. So for every value of x, are the errors for y, are they distributed the same? Do they have the same variance? So let's go ahead and click on graphs. We'll go to legacy dialogues, and then click scatter/dot. This time we're going to use a scatter plot matrix, so we're going to click matrix scatter, and then we'll go ahead and click define. And again, holding the shift key, I'm going to click down to y3 so that I could just put all of my variables all at once into the matrix variables box. Okay, I could just go ahead and click OK here, and it will create my scatter plot matrix. Okay. So what I'm going to do first is I'm going to double click to open up the chart editor. I think the points here are a little too bulky, so I'm going to go ahead and change those. So I double clicked on the dots, or the points. You can click on any point or double click on any point and it will open up this properties box. So the type is fine. I'm going to change the fill to black, and I'm going to just make the points a little smaller. I'll click apply, and then I'll close this, and then I'll close the chart editor, and it will update my chart in the output. Okay, it's still a little small, so I'm going to go ahead and resize this by dragging this out. And then I'm going to go ahead and drag this down a little bit. Okay, there we go. That's a little bit better. All right, so this is a really useful tool. It's similar to a correlation matrix, but instead of correlations, it produces scatter plots, which is pretty nice. So you have the variable names here along the columns, and then you have them along the rows as well. So the way that you could read this is, let's say we're interested in x1. So we would look at this column or this row, and if we're looking at the column, so this is x1 and y3, the scatter plot for those variables, x1 and y2, x1 and y1, and then x2 and x1. Okay. Now what we're most interested in is how the predictor, or how the variance of the residuals, how it changes or is equal across different values of the predictor. So the scatter plots we'd be most interested in looking at are any of the x's against any of the y's. But the way that I set up the data set is that x1 goes with y1, x2 goes with y2, and then y3 is just an extra y variable, and there's no corresponding predictor to that variable. So when looking at, let's say, x1 and y2, when we look at that, as we go across the x-axis, the variance of y2 seems to be equal. It's roughly equal. There's no distinct pattern that we can tell from this scatter plot alone. Okay, let's say that I want to look at, let's see, what about x1 and y1? So if I want to look at x1 and y1, here we see that there could be a potential violation to homoscedasticity, because as the values of x go from the left, which are lower values of x, to the right, which are higher values of x, the variance in y seems to increase. So here seems to be lower variance because the points are more tightly clustered together. But as we go to as we get to larger values of x, the points start to spread a little bit more. And so this is what we call a megaphone shape. And a megaphone shape is indicative of a violation to homoscedasticity. And remember, we're interested in the way that the errors are distributed across the values of the predictor, but one way to get a proxy to that is to look at how the variance of y is changing along the different values of x. Okay, so again, as we take a quick look at these scatter plots, we can see there are some megaphone shapes here. This seems to be, there might be heteroscedasticity here. But this is kind of what we want. So if you look at x1 and x2, I know we're not interested in that scatter plot because it's two predictors against each other, which is not what we're focusing on right now. But this is kind of what we want to see, is just across the values of x1 that the spread of x2 seems to stay the same and isn't changing. Okay, so that's how we look at homoscedasticity. What we're going to do next is we're going to look at assumption 4, which is independent errors. And the way that we'll do that is we'll first run a regression model, and then we'll save the residuals, and then we'll plot those residuals against the predictor to see if there are any patterns in the scatter plot. So the first thing we want to do is we'll go back to our data set, and then we'll go to Analyze. Then we'll go to Regression, Linear, and then what I want to look at is x2 predicting y2. Again, our dependent variable is y2, and then our predictor is x2. And then we're going to go ahead and click on Save, and we want to save our unstandardized residuals. So these are just the raw values of the residuals. Click Continue, and then we'll press OK. All right, so we get all of the normal stuff with our regression, but we're not interested in that right now. All we care about are the residuals. And so we're going to plot those. So again, under Legacy Dialogues, scatter/dot. This time we're going to pick a simple scatter plot. And then we want to plot on the y-axis. We want the unstandardized residuals. And then we want our predictor on the x-axis, which is x2. Go ahead and click OK. Okay, so what we're looking for here is we want the scatter plot to look random. If there is a pattern that emerges from the scatter plot of the residuals and the predictor, then it is likely that the errors are not independent. So in our regression model, we are looking at how much variance is accounted for in y by the predictor. So after we account for that relationship, there should be no further relationship that extends beyond our regression model. And if there is a relationship, as shown in the scatter plot between the predictor and the residuals, then that indicates that our errors may not be independent. Okay, so one way to kind of get a better sense for if there's a pattern here or not, because visually we can see there's this kind of U shape here. But if we really want to get a better sense, what we can do is we can double click on this chart. And then there's this small little icon here that says add fit line at total. And so I'm going to click that. And then instead of linear like we've done before, I'm going to go ahead and pick low S. So low S is a non-parametric line, and it tries to capture any of the trends in the data. So I'll just go ahead and stick with the default 50%. The kernel can stay at the default, and then we'll just go ahead and click apply. And then we'll close this. We'll close the chart editor, and it'll update our chart and our output. And as you can see, the low S line is kind of showing this U pattern here. So what that's indicating is that there could be a violation of the independent errors assumption. Okay. So moving on to the next assumption that we're going to check. We want to check for the distribution of the errors. Now again, while the assumption is more about the errors and how the residuals are distributed, we can get a proxy or a sense for what's going on with checking the distributions of the outcome variables. So I'm going to go to graphs. And the variables that we were interested in earlier from our descriptive statistics were y2 and y3. So I'm going to go ahead and click histogram. And then first I will print a histogram for y2. And then I will go through the same process, histogram for y3. So for y2, we have a little bit of a skew here, but I mean, it's not too far from normal. And then for y3, the skew seems to be a little bit worse. Because as we can see here, it kind of tapers off on the left side here, and then on the right side, and it seems like we have this one point out here, which is causing the positive skew. But for y3, it looks like it doesn't taper off here to the left, and so it seems to be a little bit more positively skewed. Yeah, so we can see here that our variables are a bit positively skewed, but it may not be that bad. And then just to check, since we have run the model and we have saved the residuals for y2 after accounting for x2, I'm going to go ahead and create one more histogram, but this time I want to look at the distribution of the residuals. Now remember, this is for the model. These are the residuals that come from the model predicting y2 from x2. And so you can kind of see here that by looking at the distribution of y2, we can kind of get a similar shape where it looks kind of normal with one of these points out here, which is kind of causing the positive skew, but the distribution of the residuals is very similar to that of the outcome variable itself. Okay, so far what we've done is we've just done a quick check for a couple of our assumptions here. So we looked at assumption 3, which is homoscedasticity, and in some of our plots for the scatter plot matrix, we saw some megaphone shapes, which indicate that the variance of y, or the residuals, is what we're actually trying to get at, that the variance of the residuals, or y, are not constant across the values of the predictor. And so that would be a violation of homoscedasticity. Assumption 4, we were looking at the independent errors assumption, and based off the scatter plot of the predictor and the residuals, there seemed to be a pattern in that scatter plot, which is indicative of a violation of independent errors. And then finally, we looked at the distribution of a couple of our y variables based off the skew and kurtosis values in our descriptive statistics to see how those criterion variables were distributed. So remember, this is just a quick first check. It's what I call my first line of defense. And then given some of the clues that we gathered from our plots, we would follow up with some more formal tests of violations to these different assumptions. And so we will cover those in the regression diagnostic, the videos for regression diagnostics. And so with that, that concludes this video on checking regression assumptions in SPSS.